This talk is called Busting Redteam Trends with Style, Lessons Learned from Building an ETW-based Sysmon replacement from scratch. This is Philipp. My name is Sebastian. We have a third of us who can't be with us today, Dominic Phillips. We are members of the CSERT of the Deutsche Bahn AG. We like trains. And Philipp and me, we are both former Redteamers who recently switched to the blue side of things. Why this talk? Defenders of you might know, without reliable and context-rich telemetry, we couldn't be doing our job. We couldn't be writing detection rules. We couldn't hunt down attackers or attacker activities, and we couldn't be doing incident response. The thing is that different sensors have pros and cons. The biggest issue is that defenders have to trust third-party sensors and cannot customize the sensor, which means that we cannot add new events to the sensor. We cannot enrich existing events. And most unfortunately, we have to trust that the sensor actually does what we think it does to reliably collect and forward telemetry, which can make our life actually very difficult. For example, if we take a look at this network event where it says that one DLL was connecting to the internet and we're trying to understand why, it would be really great if we had the command line of run DLL, which is unfortunately not included in event ID number 3. So we kind of have to correlate event ID number 3 with event ID number 1, where the command line is finally included. And this can make our Splunk queries a little bit difficult and complex. This is a very easy example, but they can get very complex when we have to join multiple events together. And as we do not have access to the source code of Sysmon, we cannot customize the event, right? If we had access to the source code, then we could add the command line to event ID number 3. Now we might be saying, oh yeah, why aren't you not using MDE? It has way more rich data, and this is great. It allows us to build way more complex detection rules. There's one big issue with MDE, however, and this is called event sampling. Event sampling basically means that it is up to MDE if an event is forwarded or not, and the criteria for this is completely opaque. MDE decides internally if an event is forwarded or not based on criteria we don't know. For example, it might not forward an event if MDE thinks this event is not very important, or there are too many events, or whatever else. We don't know, we don't have the source code, we have to trust the vendor. And the issue is that with unpredictable telemetry, we can basically not write reliable detection rules if we do not know which data we have. One word about callstacks. MDE does not give us any telemetry about callstacks. Sysmon has at least one for event ID number 10, process access, which is a shame because having access to callstacks would allow us to write very sophisticated detection rules, but neither MDE nor Sysmon has a very good support for callstacks. So the goal of our project was basically to have the best of both worlds. So we want to have a customized security sensor, which is under our control, and which allows us to fine-tune the events to our needs. We want to be using our security sensor alongside MDE, because we still want to use it for things such as incident response, client isolation, and these kind of things. We want it to be implemented in userland, as Sysmon is, simply for stability reasons. And the events that we emit must be compatible with Sysmon because we do not want to rewrite every single SPL rule we have, simply because we are now using another sensor. And now Philipp is going to talk to you about ETW, how we tried at first and completely failed on the first try.
All right, so now I'm going to explain ETW in 2 slides. ETW by itself nowadays is a high-speed communication mechanism. But it was originally developed to be a logging mechanism to do some troubleshooting and diagnostics. And the cool part about ETW is that you can consume events in real time. And developers can decide where an event may be generated. So for example, someone at Microsoft can decide that in the kernel, if someone is creating a file, for example, then an event is being generated. Each event has an event ID. So for example, process start events have a different event ID than image load events. And yeah, event IDs are predefined by developers, which means that we can't change anything about them. So for example, if there's a process start event and the command line would be missing, there would be no way for us to add this command line to the event. We can do some minor configuration about ETW events, but that's about it. ETW events contain the payload itself. like the command line for the process start event, and all EDW events have metadata such as the PID that specifies which process is responsible for the event generation and the timestamp of the event. There are kernel and user providers, and the difference is the origin of the event. So for kernel providers, events are being generated in the kernel itself or on a kernel driver. And for userland providers, it's a userland component such as a running process, a DLL, or an XC. And of course, this part is prone to tampering because you can just patch the ETW event right. So now we're all ETW experts, nice. And we basically try to implement all Sysmon events using ETW. And for that, we used commonly known providers, such as the ones listed right here. And we just wanted to see if this idea actually works. Yeah, it didn't work. We ran into many issues, and I'm going to explain the most interesting ones over the next slides. So for us, performance is really critical because we want to roll this out to production systems. And due to high CPU load, when we have to hash stuff, yeah, we had to do some optimizing. Also, we had missing telemetry. So for example, we couldn't implement some events. And sometimes we had telemetry, but it was inconsistent. And we also had a challenge for short-lived processes because sometimes we have to access a running process, and if it's gone, well, data is gone as well. So some of you may know Sysmon event number 7, the image load event. It contains file hashes for the image that's being loaded, and it's also one of the most common events. And since we have to do hashing, it's also one of the most CPU-intensive events that you can have. And yeah, we need some optimization for that. And since Sysmon is kind of our role model for this in regards to performance, we checked Sysmon, how it's handling stuff. And there seems to be some kind of caching mechanism in place. Because if you're rebooting your machine and you're starting MS Edge, for example, you can see that it's using, for example, 10% of CPU time. And then you're closing Edge and starting it up again, it will consume 0%, which indicates that the image hash will be cached somewhere. And there needs to be some mechanism in place to invalidate the hash entry in case someone is changing the DLL on disk. So we thought about that, and we kind of stole the idea and implemented a similar cache mechanism ourselves. And we really quickly ran into a race condition. Imagine if you have a DLL on disk, you're changing it, and in the next millisecond someone is loading this DLL. Then there's a possibility that in the generated event there's still the old image hash present because the information that the DLL was changed wasn't yet propagated to Sysmon or our sensor. And yet this seems to affect Sysmon as well. Basically, we saw that in our own tests. And that's a typical issue with ETW because you're basically standing on the side and watching things happening, and you don't have any hooks, for example, so you're basically dealing with old information all the time. Yeah, short-lived processes, they are a challenge because in the process create event, for Sysmon event ID number 1, there are fields like the current working directory or the logon UID, and the ETW providers that we're using, they don't supply these values. So we had no other choice than to determine them dynamically by accessing the process, which of course is not guaranteed to work, and we have a timing issue again. And missing telemetry, for example, there's Sysmon event ID number 2. I've called it time stomping. It's happening if someone changes the file creation date to an old timestamp, for example, and there's basically no event that you can use to create such an event from ETW. The same is happening for named pipe events. There's no dedicated event that you can use, and we thought really hard about this problem because named pipes are, at least for our use case, really important. And there's the object manager trace, which we can use in theory to detect named pipe creations or connects. But in practice, it will result in high CPU load. And that's happening because named pipes are treated like files in the kernel. So if you're looking for named pipe events, you're basically getting all file events as well. And 99% of them are trash for us, and we have to throw them away. And basically, there's no way to do efficient pre-filtering. So we thought about this, and we asked ourselves the question if ETW is still the way to go for us. If you look at security products, you can see that they are always using kernel-level telemetry, like MDE, for example. And essentially, they are leveraging kernel callbacks, which provide rich telemetry, which is also really reliable. But we don't have access to this information, but we kind of need it. So there's basically a way for us that we could get this information by using the Sysmon driver, which is already tested, it's existing, it's signed. But if you're looking at terminal servers, for example, which have many users being logged on at the same time, we ran into performance issues. So we currently are unable to run this driver on these systems. And yeah, we don't feel like creating our own kernel driver because of blue screen issues. So in our world, it would be ideal to find an existing kernel driver that gives us telemetry relevant for threat hunting, and the kernel driver should emit events using ETW. So we were looking for one. In ETW, there are many provider types, and one of them is the manifest-based provider. It's basically based on an XML schema that you can read and parse. And the schema defines what kind of events are being generated, how they look like, and so on. So the next idea was to export all of these XMLs and just grab for interesting stuff. And interesting stuff in our case are events related to registry, because that's the biggest pain point for us. So yeah, we just grabbed for Hive, registry Hive, and we got quite a few matches. And one, the Microsoft Windows SEC provider, looked really interesting based on the schema definition. It's implemented in a kernel driver, which is obviously signed, is provided by Microsoft, but it's not loaded by default. And it's related to a service called Sense, which is also not running by default on Windows systems, but it's defined. And we found out that this service is running in case you're onboarded in MDE, which is no issue for us because we have MDE. And you can't start this service on your own. If you try to do it manually, you get a permission denied error. We found that this provider gives us raw telemetry, which may solve our problems. Yeah, but we got another problem. We can't even access it. Even a system, if you try to open it, it says you need to be admin. And we looked into it, and we saw that you need a Microsoft signed binary to be able to access this one. So yeah, we don't have one. We don't have any binary that's signed by Microsoft that's under our control. So we had the idea to let Windows open the provider for us. And there's a feature in Windows called autologger. These are special trace sessions that are being started at boot. And yeah, it's basically being used to do system tracing and diagnosis starting from the boot process onwards. And since autologgers are started by the kernel, it passes the permission check. So yeah, permission check is not existent for us anymore. So we defined the autologger, we performed the system reboot, and now we had access to the telemetry. And we saw that this telemetry is similar to Sysmon telemetry, but it has an important difference. It forwards events to us using ETW instead of using IOCTL calls. And it turned out that our multi-user systems already had this one running. So performance should be good as well. And the telemetry itself, it looked quite good because we had named pipe events, time stomping info, we had call traces. It did no sampling, so we had raw data. And the process start events already included all three hashes that we need, so we get them for free. To actually use it, we use the Krebs ETW library provided by Microsoft. They're using it in their O365 environment in production, so that looked like a good candidate. But it wasn't possible to open an existing trace using this library. So yeah, we forked it, we've changed it accordingly to our needs. And yeah, we've open sourced it, so you can now use it. Documentation is ETW style, so there is none. Have fun. Maybe we'll do it in the future, I don't know. We also implemented kernel level filtering, which means that we're able to filter for IDs, PIDs, flags, and the event payload itself directly in the kernel. So we don't have to do it in our user space application. So these are some examples of the process create telemetry. As you can see at the bottom, there's the SHA hash already included, command line and everything. We have create remote thread events, for example, and name pipe events, including the pipe name. But we still had issues, especially for registry events. So the manifest of this provider defines registry events that should be generated, but in reality, they weren't present. And we looked into that and we saw that there's a bit field the driver is using to configure the ETW provider, and the bit for registry events is 0, and we can't change it. So we're guessing Microsoft is still testing stuff. We don't know. Maybe it will be enabled in the future. But as of now, we can't get any relevant telemetry for registry using this provider. But we found an alternative that's working quite well for us. It's called the Microsoft Anti-Malware Engine provider. It's not raw registry data, it's behavior-based, so we're getting events that Defender thinks are relevant, but as of now, it's good enough. And of course, registry key renames are still an issue.
All right, thank you. Following the research which Philipp was just introducing to you and using the SEC provider, we were able to write our own security logging mechanism, which we call Weasel, which is short for Windows Event and Security Logging. It uses the SEC provider as the baseline of telemetry. So every time there's a process started, we get informed about this using the SEC provider. We get the SHA hash and so on from it. And but we're also using additional providers, which we still need for events which are not implemented in the SEC provider. But we enrich those events with information about the respective process, of which we have the information gained via the SEC provider. Currently, we are supporting 22 enriched and customizable events, which basically includes all Sysmon events there are, except some fields in the registry. But we also introduce additional events such as AMSI, RPC, .NET assembly loaded, and these kind of things. Similarly to Sysmon, Weasel runs as a background service and writes into the Windows event log, so we can forward it to Splunk. The event filters are configurable via a config file, which is very similar to Sysmon. And in the future, there will be, of course, way more events. Taking a look at some of those events, on the upper left screenshot, we see that there's an image load event. We have every field that Sysmon is implementing, but we also have the call trace, which led to the library being loaded. On the lower screenshot, we see that the event ID number 3 is finally contains the command line of the process, which was our initial issue. And on the right side, we see an RPC event, which does not only contain the call stack, but also things such as the procedure number, which is called, or the interface UUID. So for now, what we have is we have a stable architecture. We can use different ETW providers, and we have every information about the processes we need to enrich our events. This means for us that the SPL queries we are implementing are now way simpler because our events are way better enriched than those of Sysmon, because we are able to include every information we have about the process, such as the command line or CVD or these kind of things. But we are also able, since this is our sensor, we are also able to include stuff such as information about the parent process or the grandparent process if we need them to understand a certain event. But we are also able to add additional information, such as context fields to existing events. So for example, we have an isManaged tag, which basically is added to the event and which lets us know if a process is managed or not, which might be super helpful if you're trying to analyze a call stack. But there are also built-in fine-grained detections, which we are calling IOC tags. I'm going to talk about them in a second. Our config, where it's very similar to Sysmon, except that it's implemented in JSON. We do support Boolean operations such as and, or, not, and these kind of things. Per field, we can say it must start with, end with, does contains, not contains, and these kind of things, so very similar to Sysmon. But also, per event, we can enable what we are calling detections or modules for detections. So for example, for an image load event, we activate a module which is meant to detect a technique which is called module proxying, and for other events, we are right now trying to, or we are activating modules which are meant to detect direct or indirect system calls. Let us talk about those built-in detections. Many offensive techniques can barely be detected using Splunk rules alone because they are way too dependent on the endpoint. For example, if you're trying to do callstack normalization in a larger environment, it's a task which is near to impossible to do because there are many different Windows builds, and the offsets in the NTDLL, of course, they're always different per build. In other cases, the IOC footprint is way too small, so we would have to sum up additional events and to introduce a bigger IOC, which would again require a lot of correlation, which means, again, we would have to save a lot of stuff in Splunk and make our SPL queries way more difficult. But as we have a custom sensor, which is a great thing, we can detect and correlate on the endpoint itself, so we could be doing the callstack analysis on the endpoint itself. For taking a process access event, for example, it happens quite a lot, even with a kind of suspicious access mask, but we can only store a limited amount of events. Yet, there are many evasion techniques which attackers came up with introduce unnecessary IOCs and which we are trying to detect on the endpoint and forward the event if we detected something fishy going on. For example, a direct system call detection, it's very simple. If we do see that the last module in the call stack to open process is not NTDLL but something else, then we do add an IOC tag saying, hey, this call stack looks like it was using there's a direct system call going on here. Similarly to direct system calls, indirect system calls, where it is abused that not every system call stub in NTDLL is hooked, and attackers are reusing a non-hooked stub, but with an unexpected system call number. And here, in the screenshot, we see that a program was calling NTDLL execution, yet in the call stack, we do see that the stub of NT-open-file was used, which doesn't make any sense because we have a huge mismatch here. And if we do see something like this, then we can also add an IOC tag saying that this looks like it was an indirect system call, which we have observed. And we do this by building a static list of system call offsets in NTDLL, stubs who's related, which we expect to see when a certain event happened. And if we do not see that stub which we are expecting, then we're saying this might be an indirect system call. And we add this to the event itself. Talking about image load events, there are a couple of DLLs which are usually loaded by both C2 beacons and other offensive tools, such as WinEnet, NetAPI, and these kind of things. And as these tools are usually protected by a packer in order to circumvent static signatures, you usually have a private page in the call stack to kernel 32 load library, which certainly is an IOC, so we can add an IOC tag saying, hey, this call stack contains a private memory page. And what attackers are usually doing to bypass this is that they proxy the call to load library through NTDLL using worker threads from a thread pool. And what is happening internally is that a separate worker thread picks up the work item and loads the DLL into the process, which produces a kind of clean call stack without suspicious pages because the worker thread is not related to the code of the beacon. But is it really that good? On the left side, we see how load library is usually being used. So we see that if load library is called, it internally calls LDR load library in NTDLL. So the Windows API is calling the NT API, which is a perfect fine thing. But if you're using work items, we see that the NTDLL is calling into the kernel 32 DLL, which then once again is internally calling LDR load library. And this is quite odd because in this moment we have a shift from the NT API to the Windows API, which doesn't make a lot of sense as the Windows API is an abstraction layer for the NT API, not the other way around. So we can see this in the call stack, and on the left side we see a normal call to load library where something ended up calling load library implemented in kernel base, which then calls the NT API internally. On the right side, we do see, however, that something in NTDLL is calling kernel base, which contains the load library, which then once again is calling NT API. And this sequence of call is so rare that we can actually say with a very low false positive rate, if we detect such a call stack in an image load event, then we can add an IOC tag saying this looks like module proxying to us, and forward the event because we find it especially interesting. But that's not everything we do. We implement something we call process rating, which means that we observe the behavior of a process for a longer time. So for example, we record if the process is talking to the internet or to the intranet at the same time. If it loads certain DLLs, and if a certain threshold is hit, then we report the process as such because it looks like an offensive tool or an injected beacon. Additionally, processes are periodically scanned for IOCs, such as abnormal memory allocations or thread states. Why thread states? It's because HTTP-based beacons usually wait between the callbacks, and now the idea would be to enumerate all idling threads and check the call stack to the blocking function. And if you find an IOC in this call stack, it also influences the process rating. So for example, on the upper screenshot, we see that a thread is idling and the call stack to NT-delay execution contains two very odd values. The first is not even an executable page, and the second is a pointer to a private committed memory area, which is a huge IOC that there's an injected beacon. The second screenshot shows again a thread which is idling, but we identified a module which is not the same module as it is on disk, so we can assume that a beacon or another tool loaded this DLL and replaced the content of this legitimate DLL with itself. This one is not a strong IOC. It's probably the least, like the smallest IOC in this technique because it happens quite a lot that processes are changing the DLLs. Speaking about sleep masks, I'm not going to get too much into details for timing reasons. It is important, however, to understand that APC-based sleep masks, at some point, they trigger a sequence of APCs, and one of those calls a blocking function. And this is quite odd, because an APC basically tells a thread, hey, while you have nothing to do, I give you another task. And if an APC says, hey, while you have nothing to do, please wait for 5 minutes, this doesn't make a lot of sense. So if we see that a blocking function was called and we see the KI user APC dispatcher on the call stack, then we can, with a high confidentiality, say that there's something going on. Same goes for timer-based sleep masks. Timer-based sleep mask, once again, they're using timers, one of which ends up calling a blocking function. Here the thing is that even MSDN says, if you use timers, then please don't make them block, because you're going to ruin your own thread pool. So if we do see the RTLP TP timer callback in a call stack to a blocking function, then we can also consider this an IOC. The idea to check for this callback on the call stack is not ideal because we do not find pending timers. We only find those timers who already fired. And this leaves a big detection gap, and CobaltStrike's call stack masker currently bypasses this. And in order to find projects like these, we would have to enumerate all pending timers and the callbacks, which is not an easy task since timers are barely documented and thread pools on which timers are built on, they're also not officially documented. They're not officially documented, however, Safe Breach Labs a couple of months ago released a really cool tool which they call Pool Party, in which they make use of a very clever technique to inject into another process. With this tool, they also released structs on timers and thread pools. I don't know where they have them from, but I'm very glad that they released them. Because using those structs, it is actually possible to enumerate pending timers and their exact callback. And if we do find a pending timer, which callback points to a function which is usually executed by a beacon or by a sleep mask, then we can, with a very high confidentiality, say that there is a beacon which is using a sleep mask injected into the process. And this is really cool. We are now able to enumerate every single pending timer and the callbacks, and this currently finds most of the implementations of timer-based sleep masks because we're able to enumerate them very precisely. It of course depends on which function the callback executes, because we can only match on callbacks or functions of which we know that sleep masks are using them. The severity here is quite critical, and we do see that here that callstack masker of Kobold was actually found using this tool. As you see, callstacks are extremely valuable for defenders, and it's not a surprise that attackers are, of course, trying to spoof their stacks. There are many proof of concepts. Probably the best one is Silent Moonwalk. But most of those which I found, they make use of a ROB gadget, which jumps to a non-volatile register. And guess what we can do? We simply iterate through the call stack and try to see if we find a return address which points to such a gadget. And if we have a match here, then we could also report this process. If we put all of this together, then we see in this screenshot echo.exe, which is one of the most popular or well-known sleep masks there is, and we have different findings, such as an exact timer, which we found, which points to NTDLL, NT-continue, but also many others, so this process would certainly hit the threshold for us to report it. A year ago, I released a proof of concept for this, which I have heavily updated for this presentation. And yeah, you're free to play with it and let me know your results. It should find most of those timer-based sleep masks currently. Okay, in summary, we were way quicker than we thought. That's okay. So in summary, what is important to understand is that relying on third-party sensors is challenging for us as defenders because we cannot customize the events and we have to live with those events that we have. If you want to build your own ETW provider, then you need to understand that well-known, if you want to write your own sensor, you need to understand that well-known ETW providers are not always meant to be used for threat hunting. We did find a way to use raw sense telemetry, which is great, and we built our custom sensor based on this SEC provider, which requires an MDE on board the device, but as we were saying in the beginning, we want to be using both at the same time, so that's not an issue for us. The events of our sensor are customizable, and we introduced fine-grained detection mechanisms for things such as module proxying, direct and indirect system calls, but there are, of course, way more to come in the future. We have a static scanner, or we have a built-in scanner to detect C2 agents. And what is going to happen in the future is that we, of course, need to think about how to protect our own ETW session and our sensor itself. We are already doing this, it's just that we don't tell you how. And of course, in the future, we're going to implement way more events to make our sensor even better. That's it, and thank you so much for your attention. You are now free to ask any questions.